When we take ice cubes in a glass, without any external intervention, there is a melting of ice cubes into water. It's a spontaneous process. Suppose if you take the reverse process, that is conversion of water into ice, it is not possible without any external intervention. It's a non-spontaneous process. When we take a cup of hot coffee, it releases heat into the surroundings. But the same heat cannot be transferred from surroundings to the cup of coffee. Let us take a scent bottle at the corner of the room. When you open the scent bottle, the scent molecules diffuses throughout the room uniformly. It's a spontaneous process. If you take the reverse process, that is concentration of scent molecules at the corner of the room, it is impossible without any external intervention. It's a non-spontaneous process. In these days, we are familiar with lockdown, the term lockdown. The process of lockdown is not possible without any external intervention, that is government intervention. But if you take unlock process, the unlock process is a spontaneous process. It takes place without any government intervention. So in this case, lockdown is a non-spontaneous process. Unlock is a spontaneous process. So in all these cases, in one direction, the process is spontaneous. In reverse direction, the process is non-spontaneous. The process is spontaneous in the direction in which there is a dispersion of energy or matter, or there is an increase in disorder. A thermodynamic function which measures the dispersion of energy or matter or direction of increase in disorder is entropy. Entropy is a thermodynamic function which can predict spontaneity of a reaction. So in this lesson we will discuss a concept of entropy. In this lesson we have what is the background of entropy, what is the definition of entropy, and change in entropy in different processes, and physical significance of entropy. Let us take background of entropy. In 1820s, Nicholas Sadikan worked on conversion of heat into work. He declared that heat flows spontaneously from hot body to cold body. He also declared that cold bodies never export coldness, but hot bodies exports hotness. In 1840s, James Prescott Joule worked on conversion of work into heat. He proposed a principle, mechanical equivalent of heat, in 1845. According to this principle, the mechanical work can be converted into equivalent amount of heat. In 1850s, Kelvin worked on both conversion of work into heat and also heat into work. He realized that both work and heat are different forms of energy. According to him, the whole heat cannot be converted into work. There is a dissymmetry in nature. The whole work can be converted into heat, but the whole heat cannot be converted into work. He also proposed two principles. The first one is conservation of energy. According to this principle, energy neither be created nor destroyed, but it can be transformed from one form to another form. And the second principle is dissipation of energy. According to this principle, energy is conserved, but the energy available for do work is degraded. Later, Rudolf Clausius, he worked on both conversion of heat into work and also work into heat. He was the first person to formulate laws of thermodynamics based on principles proposed by Kelvin. In 1850, he proposed first law of thermodynamics. It deals with the conservation of energy. According to him, you cannot transfer heat from cold body to hot body. It is highly impossible. But it is possible when you do some work on the system. There is a possibility of transfer of heat from cold body to hot body. He is the person who coined the term entropy, which predict the spontaneity of a process. And according to him, entropy measures degradation of energy or unavailability of energy. In 1865, he proposed second law of thermodynamics. According to this principle, in all spontaneous process, there is an increase in entropy. It means the spontaneous process takes place in the direction of increase in entropy. And also he proposed an inequality, that is Clausius inequality, for cyclic processes. If you take reversible cyclic process, the integral dq by t is equal to 0. It means the change in entropy in reversible cyclic process is 0. If you take irreversible cyclic process, like cyclic process consists of irreversible processes, the integral dq by t always less than 0. So if you take any cyclic process, the change in entropy or integral dq by t should be less than or equal to 0. Later, in 1877, Ludwig Boltzmann defined entropy in terms of probability. According to him, the entropy increases with increase in disorder. The spontaneous reactions takes place, or the spontaneous process takes place in the direction in which there is an increase in disorder. Definition of entropy. Entropy can be defined as unavailable energy per unit temperature. So S is equal to unavailable energy by temperature. The microscopic definition of entropy is given by Boltzmann. According to him, S is equal to K into ln W. Here K is Boltzmann constant and W is thermodynamic probability. The change in entropy, that is delta S, is equal to Q reversible by temperature. In terms of enthalpy, the change in entropy of the system is equal to plus delta H by T system, and the change in entropy of surroundings, delta S surroundings, is equal to minus delta H by T surroundings. The change in entropy of universe is equal to sum of change in entropy of system, and change in entropy of surroundings. The standard entropy of an element. It is the molar entropy at 298 Kelvin or 25 degrees centigrade and 1 atmospheric pressure. If you take standard entropy of any element, should be greater than 0. Units of entropy. The units of entropy are equal to the units of energy divided by temperature. So the units of entropy is Joule, Kelvin inverse. If you take a specific entropy, it is the entropy of 1 kg substance. So the units will be Joule, kg inverse and Kelvin inverse. If you take the molar entropy, it is the entropy of 1 mole substance. So the units will be Joule, mole inverse and Kelvin inverse. The concept of entropy can be derived from Carnot cycle. The efficiency of Carnot engine, eta is equal to QH minus QL by QH is equal to TH minus TL by TH. So it can be written as 1 minus QL by QH is equal to 1 minus TL by TH. That implies QL by QH is equal to TL by TH. That implies QL by TL is equal to QH by TH. When you apply sign convention, for QH the sign is positive and for QL the sign is negative. So the equation will be minus QL by TL is equal to plus QH by TH. That implies QH by TH plus QL by TL is equal to 0. So from the above equations, we can write two general equations. The first one is Q reversible by temperature is equal to constant, and the second one is Q1 by T1 plus Q2 by T2 is equal to 0. Let's take a cyclic process, that is ABA, consists of AB process and BA process. If you take ABA cyclic process, it can be shown with the infinity number of Carnot cycle. We know that the efficiency of each Carnot cycle, according to efficiency of each Carnot cycle, we can write Q1 by T1 plus Q2 by T2 is equal to 0. Suppose if you take infinity number of Carnot cycle, the sum of Q by T times will be equal to 0. So when the changes are infinitesimal, the Q is equal to dQ. So the equation will be sigma dQ by T is equal to 0. If you take the processor, it consists of AB process and BA processor. So it will be equal to integral A to B dQ by T plus integral B to A dQ by T is equal to 0. That implies integral A to B dQ by T is equal to minus B to A dQ by T. So the first one indicates the change in dQ by T along the path 1, and the second one indicates the change in dQ by T along the path 2. In this case, the change in dQ by T along path 1 is equal to the change in dQ by T along path 2. So the function dQ by T is a definite function and it's a state function. It is defined as entropy. The term dQ by T is defined as entropy. So here delta S is equal to SB minus SA is equal to integral A to B dQ by T. Suppose the change is infinitesimal, then delta S is equal to ds. So the ds is equal to dQ by T. If it is finite, the ds is equal to delta S and dQ is equal to Q. So the change in entropy delta S is equal to Q by T. delta S in different processes. In isothermal expansion or compression of gas, the change in entropy delta S is equal to nR ln Vf by Vi is equal to nR ln Pi by Pf. Cooling and heating. In isobaric process, the pressure is constant. So the delta S is equal to Ncp ln Tf by Ti. In isochoric process, the volume is constant. Here the delta S is equal to N into Cv ln Tf by Ti. In isobaric process we have Cp term. In isochoric process we have Cv term. And delta S can be written in terms of T and P. Then delta S is equal to Ncv ln Tf by Ti plus Nr ln Pi by Pf. When you write in terms of T and V, the equation will be delta S is equal to Ncp ln Tf by Ti plus Nr ln Vf by Vi. If you take phase transitions, in this case, the change in entropy is equal to enthalpy change for each transition divided by temperature at which the transition takes place. So if you take entropy of fusion, delta S fusion is equal to delta H fusion by melting point, that is Tm. Here delta H fusion is equal to enthalpy of fusion, and entropy of vaporization, delta S vaporization is equal to delta H vaporization by Tb. Here Tb is boiling point, and delta H vaporization is equal to enthalpy of vaporization. Physical significance of entropy. Entropy measures disorder or randomness. Physical significance of entropy. Entropy measures disorder or randomness. Physical significance of entropy. Entropy measures disorder or randomness. We know that from solid to liquid and liquid to gas, there is an increase in disorder due to increase in movement of molecules. So from solid to liquid and liquid to gas, there is an increase in entropy. When you increase temperature, there is an increase in kinetic energy of the molecule, and also there is an increase in disorder of the molecules. So there is an increase in entropy. At 0 Kelvin, the entropy of the solid is 0. Entropy also measures the probability of a state. According to Boltzmann, entropy is equal to K into ln W. Here K is Boltzmann constant. It is the ratio between gas constant and Avogadro number. And W is the thermodynamic probability. Thermodynamic probability W is equal to probability of actual state divided by probability of complete order state. Suppose if you take a solid at 0 Kelvin. In this case, the probability of actual state is equal to probability of complete order state. So W is equal to 1. When W is equal to 1, ln W is equal to 0. So S is equal to 0. So if you take ideal solid, it means a solid at 0 Kelvin temperature, the S0 is equal to 0. According to third law of thermodynamics, as the temperature approaches to 0, the entropy approaches to 0. At 0 Kelvin, the entropy of ideal solid is 0. Suppose if you take a bulb containing 2 gas molecules, when you remove stopper, the 2 gas molecules will be distributed uniformly. It means each bulb contains single molecule. Here if you take a first state, this one is high order state. The second state is low order state. The high order state, if you take, it has low probability, and the low order state has high probability. So the high order state has low entropy and the low order state has high entropy. It can be understood by taking different states. Suppose if you take the first state, which is having two molecules in first bulb, how many configurations are possible? How many arrangements are possible? Here only one arrangement is possible. Suppose if you take bulb with single molecule, each bulb with single molecule, here you can find two configurations, A in first bulb and B in second bulb, and B in first bulb and A in second bulb. So in this case you have two configurations. Suppose if you take the next state, that in which the two gaseous molecules are in second bulb, here you can find only one state. So here the probability is 2, here the probability is 1, here also the probability is 1. So in this case, when the molecules are distributed uniformly, the probability is more, the disorder is more, so the entropy is more. Spontaneity of a processor. You can predict the spontaneity of a processor by using entropy. According to second law of thermodynamics, a process is spontaneous when delta S universe is greater than 0. If it is less than 0, the process is non-spontaneous. The reverse process will be spontaneous in this case. When the delta S universe is equal to 0, then the process is reversible process. Suppose if you take delta S system positive and delta S surroundings positive, obviously delta S universe is positive. In this case, the process is spontaneous at any condition, always spontaneous. Suppose if you take delta S system negative and delta S surroundings negative, obviously the delta S universe negative. So in this case, the process is non-spontaneous, but the reverse process or the opposite process is spontaneous. Suppose if you take delta S system positive and delta S surroundings negative, in this case we cannot predict positive or negative. But if the value delta S system positive value is greater than delta S surrounding negative value, then the resultant value delta S universe will be positive. Then it will be spontaneous. Suppose if you take delta S system negative, delta S surroundings positive, in case also you cannot predict whether the delta S universe is positive or negative. But when the delta S surroundings positive value is greater than delta S system negative value, then delta S universe is positive. Then the process is spontaneous. And also you can derive Gibbs free energy from delta S universe is greater than 0 in spontaneous process. So if you take spontaneous process, delta S universe is greater than 0. We know that delta S universe is equal to delta S system plus delta S surroundings greater than 0. You can write delta S surroundings as minus delta H by T. So that implies delta S system minus delta H by T greater than 0. That implies T delta S system minus delta H greater than 0. When you multiply with T, you will get T delta S system minus delta H greater than 0. So it can be written as minus T delta S system plus delta H less than 0. Here you are multiplying with the minus value, minus a negative R. Then it can be written as delta G less than 0. Here delta G is equal to delta H minus T delta S system. In this case, for all spontaneous process, delta G is negative. The next physical significance is it measures unavailable energy. Okay, what is unavailable energy? Suppose if you take heat, it can be converted into work. So heat can be written as available energy or useful energy. plus unavailable energy or useless energy. The fraction of heat which can be converted into work, that fraction can be called as available energy. The remaining fraction which cannot be converted into work, that fraction can be called as unavailable energy. So available energy, that is the part of energy which can be converted to work. Unavailable energy, part of energy rejected by reversible heat engine to the surroundings. Okay, as the TL decreases, we know that as the temperature of the sink decreases, eta increases. It means W max increases and QL decreases. When QL decreases, the unavailable energy decreases, so the entropy decreases. So entropy can be defined as unavailable energy per temperature. We have an interesting phenomena which is related to entropy, that is heat death of the universe, which was proposed by Kelvin in 1850s. It is also named as Big Chill or Big Freeze. We know that according to second law of thermodynamics, for the universe there is an increase in entropy. When the entropy reaches maximum, that is the unavailable energy reaches maximum, so the available energy will be 0. The change in Gibbs free energy will be 0. In this case, the available energy to do work is 0. So we have energy, but the energy cannot be utilized for the doing work. That condition can be called as heat death of the universe. According to one study, it will be taking place in 10 to the power of 100 years. Thank you. Thank you very much.